All right, so a very warm welcome to all of you, my dear students. A very warm welcome to all of you, and I am your physics educator, Dr. Shankar Sir. I hope you guys can comfortably see me and hear me. And sorry for because after some time, because after some gap, I am coming up with a live session. So due to some personal issues, I couldn't take your live session from the last few days. I'm really sorry for that, but I am going to compensate for all of it. Okay, and today and from today onwards, I'll try to, come up with relatively bigger sessions, and in these sessions, we'll be covering, quite a big concepts in one go. We'll try to do. Okay, so guys, in this session, so first of all, let me introduce myself. I'm Dr. Shankar Tripathi. I have done PhD and MTech from Indian Institute of Technology, Roorkee, and these are some more credentials of mine. I hope the students of and the subscribers, the students who are following us were missing me, right? So, guys, from today onwards, I'll be, till now on this channel, what we have done, we have completed units and measurement, we have completed motion in a straight line, we have completed motion in a plane. One small topic is left to circular motion. Other than that, we have completed all of it. Along with it, we have completed the vectors completely. You can see detailed sessions of the vectors also. You can see complete session, one complete revision session of the vector as well, right? And similarly, we have completed motion in a straight line, units and measurement. You can see a detailed session of these and complete revision session of these topics as well, these chapters as well. Now, guys, I am going to today begin with a chapter that is your first chapter of 11th Physics Part 2. Okay, so we have done three chapters of 11th Physics Part 1. Now, I am be doing three chapters of 11th Physics Part 2, and along with that, I'll be starting with the Newton Law of Motion. Okay, okay, so guys, let's begin. So we are now starting towards the properties of bulk materials. The properties of bulk materials, and in this, the first part is the properties of solids. The properties of solids. So basically, in this particular part, guys, what we are going to talk about, what is the thing that we are going to talk about. Okay, so now see, please understand this. So till now, when we are talking about the Newtonian mechanism, Newtonian mechanics, okay, where we are dealing with displacement, acceleration, and everything. So see, it's a very simple chapter. Okay, how this chapter is different from what you have read before in the normal Newton law of motion or Newton's law, right? Okay, so see what happens. Let's suppose we are having a body. Let's suppose we are having a body, and on this body, we are applying some sort of a force. Let's suppose we are applying a force P. Okay, you can call it P, you can call it F, whatever you want. Okay, so let's call it P, right? Okay, so that you don't get confused with F is equal to ma, right? Now this P we are having here. So just a moment. So I'm really sorry. I think the voice was not there. Okay, I'll just repeat myself here. So see, what I was saying, let's suppose that there is a force on acting on this body. Okay, and when this sort of force is acting on this body, I think we can understand that it is being changing its position. It is going to show some displacement. It is going to show some change of the. It is going to show some change of the position. That is, it is going to have some displacement. Now, when it is going to have some displacement, guys, then we how we analyze this physical problem. So, sir, when it is having some displacement, we talk about the velocity. Okay, by differentiating this displacement with respect to time, we can have some velocity, right? We apply the kinematics part, then we go to the Newton's law and all, right? So when x is differentiated with respect to time, we very well know that dx by dt gives you the velocity, and if the velocity is differentiated with respect to time, we get the acceleration. We are well aware of this thing, right? A is equal to dv by dt, or a is equal to d2x by dt square. Okay, so now when the force is applied on this body, it shows some displacement, and we can do the kinematic analysis. We can apply the concept of kinematics that we have learned. Okay, we can apply the concept of kinematics that we have learned. And what are those concepts of kinematics? Sir, through the concept of kinematics, we can have the displacement. From the displacement, we can have the velocity. From the velocity, we can have the acceleration. And once we have the acceleration, then we can say, or we can apply, F is equal to ma, right? Okay, so any body which is having some acceleration, there is one force, that is F is equal to ma, acting on that body, and net force are on this body are going to be equilibrium with this particular force if it is included. Okay, net force on a body is equal to mass into acceleration, right? Or you can use a twisted form of it, that is D'Alembert principle. Okay, in another way, D'Alembert have explained this, or somehow what we believe that, what I believe, or many of the IITians normally believe this, that D'Alembert has somehow manipulated the Newton's second law. It is nearly the same, but he has presented the law in a slightly easier way. What is it? That okay, you like a static equilibrium? Okay, you do a static equilibrium, just add inertia force to it. Okay, and put it equal to 0. This is how. Ultimately, what is my point here is that whenever a body is having some kinematic terms involved, like displacement is there, like acceleration is there, like velocity is there, if anything like that happens, then the approach of our analysis goes like this, that we find the displacement, we talk about the displacement, then velocity, then acceleration. Further, F is equal to ma, right? F is equal to ma, we do somewhat like this. Okay, I hope it is fine to everyone. Right, now in this, what context we are first of all talking about? So see, when we are talking about the Hooke's law, Hooke's law is, in this session I'll be dealing with the Hooke's law. Okay, that is a very important law to understand the properties, how solids behave, right? How solids behave, right? Now in this very case, see, when this body is applied with a force like this, it has displaced from one position to another. But if you are considering 2 points on this body, let's suppose like we are considering 2 points A and B on this body, having the distance between them as x1. Okay, having the distance between them as x1, right? Now when you are applying a force like this, which is causing the displacement to this very body, now in this case, what is going to happen? The position of A and B, okay, if it is x1 initially, it is not going to be change. It will be x1 only. It will be x1 only here also, isn't it? Yes, sir, definitely. In this case, see, if you consider any 2 points within the body, the relative position, or the position, the distance between these 2 points are not going to get changed if a force like this is applied to it. If a force like this is applied to it. Are we getting my point, Bida? right? Okay, okay. Now, let's assume that we are applying a force like this on this body now. Okay, the same body, the same body. Now see, so if a force is applied like this is going to change its position, and we are going to do somewhat kinematics to it. We are going to talk about mathematics involved with the displacement, velocity, acceleration, F is equal to ma and all it. Okay, but now if I assume or if I say that a force like this is applied on this body, that is P and P, force like this is applied on this body. Now in this condition, what is going to happen? So now if you feel it, so a body is there and you are kind of pulling it from both the ends, isn't it? With the same force, right? So see now what we are interested in. So what in this particular part of physics we are interested in knowing that when such a thing is happened on a body, okay, when such a thing is happened on a body, that two equal and opposite forces are acting. It can be in any direction. It can be shear also. I'll be coming to that. Okay, I'll be coming to that. So two forces are acting like this. Two forces are acting on this body, trying to pull this body. Okay, now what is going to be the behavior of this particular material under such condition? That is what we are trying to understand here. Okay, now absolutely so. When we are pulling something, when we are putting force on some body from both the ends and we are trying to stretch it, okay, now in this case, what is going to happen? Now in this case, what is going to happen? So it is going to show some elongation like this. It is going to show you some elongation, right? It is going to get stretched like we do with rubber and everything, right? Now it is going to show some stretching here, right? Now in this case, see what how it is different. So now if you believe that 2 points are there, A and B, do you see that in this condition, the distance between the A and B is changed now? Okay, okay. So position of any 2 points within the material is also getting changed. Okay, also getting changed. So this is what we call as the deflection. Okay, so initially if the length was L, initially the length was, let's suppose of this is L. Okay, initially if the length was L, now when these forces are applied to it, obviously it is going to have some change of length. Okay, have some change of length, and now the new length, this body will be assuming or will be having will be L plus delta L, or we can just write L plus delta, that is the elongation or deflection, deformation, whatever you say in this case. Okay, now in this chapter we are largely interested in this delta. Okay, this is the delta we are interested in. Our interest, our not the interest that we get from the bank, but our interest, that means our focus, our concentration, our orientation, everything happens to be on this delta, right? On this delta. Okay, okay. Now same scenario can happen in this case. Okay, so this is the same case. See, if there is a body like this, that is a fixed body on an end. Okay, it is a fixed body on this end. Okay, now when this body is fixed on this end, now see what is going to happen. If I apply a force like this P, okay, this fixing, so it is fixed from one side. So when it is fixed from one side, this is going to develop our reaction. Let's suppose that is R. It is going to develop our reaction, and we are calling this reaction as R. Okay, so what is going to be the reaction in this body? So the reaction in this body will be P only, and the direction will be this. Okay, this is going to be the direction of it. Okay, see, I am not going to teach you the way this chapter is being taught by mostly the educators, right? Because see, I am a mechanical engineer too, right, from IIT. So this is something we have learned this, we have done research on this. Lot of things we have done on it. This fluid mechanics, fluid part, thermal part, gravitation part, Newton laws part. So these are like in our heart only. So I'll give you many tricks also. I'll give you like I'll make it very interesting, right? You don't need to worry a lot. Okay, so free body diagram we have to make this, we have to do that, we have to do if force is applied in between, so then what happens, self weight happen, then what happened, or is a stress strain curve we never be able to understand. Okay, so you just believe me, and we are going to take care of it in a very very nice way. Okay, in a very very nice way. Okay, now the same thing, the same scenario is happening. The same scenario is happening in the case when this body is fixed from one end. Okay, we can assume that this body is having the reaction. Okay, okay, we are having the reaction. Okay, we are having a reaction also. Okay, and in this case also it is going to show some deflection like this. Okay, it is going to show some deflection like this. Okay, it is again going to have some change in dimension, change in length, which we are interested in finding out. Okay, I hope this much is clear to you. So see, if I summarize all this thing, load can be on any type also. So see, till now we have been dealing with the rigid bodies. Okay, till now we have been dealing with the rigid bodies, right? Means like in the chapter 5 of part 1. Okay, we are dealing in the chapter of rotation. In all these chapter, guys, we were dealing with the rigid bodies actually. Okay, we were dealing with what? So we were dealing with the rigid bodies. Okay, we were dealing with the rigid bodies. Now, in this case, we are not going to deal with the rigid body. So what are the rigid body in general? The live students can tell me what is the rigid body. What is a rigid body? So basically, rigid body is something. What is a rigid body? So rigid body is something. So if you apply force on the rigid body, okay, if you apply, so rigid bodies are basically. So what are the if force is applied, if oh my God, just a moment. Some technical issue. Yeah. So I was saying, so in the physics that we have seen till now, in that we particularly talk about the rigid bodies. Like for example, we have seen the rotation chapter, we have seen the Newton's law and everything. So rigid body is what? So rigid body, in the rigid body what happened? There is no change in shape and size with application of force. Okay, so when you are applying force on some solid, okay, on if you are applying, or I may say, if you apply some force on some solid, if that solid is not going to show you any elongation, any deformation, any change of shape and size, that is in physics what we refer to as the rigid bodies. And practically there is no body in this world which absolutely show no change of shape and size on the application of force. Right? So rigid body is basically a myth. Right? There's no body which is a rigid body. Okay? No body which is a rigid body. Now guys, when there is no body which is a rigid body, so under the application of force there can be change in shape and size. Okay, there can be change in shape and size, right? There can be change in shape and size, right? Like for example, what I can quote a spring, isn't it? So we have a spring, we all know a spring, right? Now when on a spring a force is applied. When on a spring a force is applied, let's suppose F force is applied, is it practically going to change its shape or size or not? Yes, sir. It is definitely going to change some shape. Okay. So in this chapter, in this particular part of physics, we are interested to know that what can be possibly the change in this shape and size, okay, which depends upon the type of force that you are applying on a body, right? Okay, so this is what we are going to deal. So basically in this part, see, we'll be talking about a few things. That is, one is the stress, okay, one is the stress, okay, uh, one is the strain, okay, one is a stress and one is a strain, right? So in this particular part we are more interested in finding out the stress and strain on a body. Okay, so let's first talk about the stress. Let's first talk about the stress. Okay, so what is the stress, guys? Okay, so let's take example of a body. Okay, let's take a example of a body. So see, let's suppose there is a body, three-dimensional body like this. Okay, three-dimensional circular bar is like this. Okay, and now I am going to apply. Okay, so let's suppose I have fixed this from this side. See, if we are talking in this part of the physics, definitely it would be either fixed. See, what we are dealing with, two equal and opposite forces. So if one end is having fixed, it will create the same reaction that of the external force. Okay, it is going to create the same reaction as that of the external force. So here we'll be talking about the balance problems. Okay, we'll be talking about the balance problems. Okay, the problems which are in static equilibrium. Right, now what does that supposed to mean? See, let's try. See, once the basics are understood, you are definitely going to excel into it. So, see, what I am referring to here, what I am trying to tell you here, what I am referring to here. So, let's suppose there is a body, and see, on this body, we are having multiple force acting on it. We are having some multiple forces acting on this body. Okay, acting on this body. Now, we very well know already that we how to take the resolution, how to take the moment, right? All this will be used in this particular chapter. Okay, I hope you are well aware of it. We previously have discussed all this thing, that how to resolve the vectors. So resolving force is also a vector you can resolve. So see, when you are seeing all these forces, it be F1, F2, F3, F4, or maybe anything like that, F4, F5, F6, right? It can be anything like that. Now, you can obviously take the component of all of these forces in x and y direction. You can take the component of all these forces in x and y direction. See what is going to be the condition for this particular of or any problem particularly lie in this zone of physics. So for that, the summation of forces in x direction must be 0, the summation of forces in y direction must be 0, and the summation of moments must be 0. Okay, this is what we call as that when this happens with a body, you can say that this is in a static equilibrium. This is in a static equilibrium. Okay. Okay, so whatever forces are acting on a body, whatever forces are acting on a body, if they are to be in static equilibrium, then only it will fall under this category. Understood? Okay, right. Okay. Now see, what is the stress? Let's talk about the stress. Now, first of all, if I apply a force like this, see, let's suppose we are applying a force here. Let's call it P. Okay, now this particular body, if I try to show it in two dimension, it may be looking like this, right? When you are seeing it from the front, and since it is a two-dimensional body, since it is a three-dimensional body, you need more than one view to describe this body. Okay, so if I see from the front, I am going to see it like this. If I am going to see from the front, I am going to see it like this. Okay, right? Okay, now when I am seeing it like this, if I apply a force, so the same force will look like this. Okay, okay, it can have a die of d or like anything, any dimension it could have, right? Now when this force is there, is it going to show you some reaction? Yes sir, definitely sir. From the, so since it is a problem of properties of solid, there must be one reaction to this P, and that reaction will be P only, because the sum of horizontal forces must be equal to 0. The sum of forces in the horizontal direction, they must be equal to 0. They must be equal to 0. So if I assume that some R is acting here, see, R is acting here. So what we need to do, so for any vector, we need to give some direction to it, right? To show the direction of it mathematically, I can assume this direction to be positive. I can assume this direction, this R direction to be positive, right? And this P direction to be negative. So what can I say? I can say that this is going to be equal to plus R minus P is equal to 0. Okay, so R is going to be P. So simply speaking, the reaction is nothing but it is equal and opposite to the net loading. It is equal and opposite to the net loading. Okay. Okay. Is it fine to you? So first thing that you need to do is find the reaction. Is it clear? Yes or no? Because in this particular part, we are dealing with when the forces are applied in such a way that they are equal and opposite on a body. Right? Now see, what is going to happen? Now when this kind of a force is going to be applied on this body, it is going to be stretched a bit, right? Like this. See, it is going to be stretched like this, right? It is going to have the stretching like this. Okay, it will be elongated like this. Okay, so initially if its length was L, the length is now increased. The length is now increased and it becomes L plus delta L. It becomes L plus delta L, or we can say L plus delta only. That is also fine. L plus delta only, right? Okay, we can say that this is L plus delta only, right? So we can say this is L plus delta. Okay, so this is L. So when the force is applied, it is going to show you some elongation, some deformation, and the length is going to be changed to L plus delta. Let's assume it is going to change to L plus delta. Okay, L plus delta. And also, see, now please observe. See, this is a very observation you have to do. So here the length is increasing to some extent, right? And you see if the cross sectional dimension, if you feel when we are, see, this is very practical thing, no? So when we are stretching on something, okay, when we are stretching on something, when we are pulling something, so when something is stretched, when something is stretched, guys, when something is stretched, okay, if its length is increasing, you can see that the diameter is decreasing, the length is increasing, but the diameter is decreasing. Understood, Beta? Okay, this is what we know as the Poisson effect. I'll come to that. Let's first focus on the Hooke's law. Okay, so see, in this case, see, there will be some stress. Okay, and that stress, if I define the stress, now please understand this. So how I can define the stress? So whenever a force is applied on a body, okay, and we are not taking care of the motion part, we are trying to see, or we are trying to focus upon the change of shape or size of the body. Okay, in the such cases, see, there will be some stress on the body, and that stress we say, that stress we are going to call it, or how we can define it. So basically stress, so whenever an external force is applied on a body, any material has a tendency, or any body has a tendency to resist that force, right? Just like us, if somebody is applying force on us, we try to resist it. Similarly, any material in this world, be it, solids, be it liquid, be it even gas, when some force is applied on it, it always tries to show some resistance towards that stress. Okay? Okay? So, how can I define it? So, it is the internal resisting force per unit resisting area, per unit resisting area. Okay, now what does that supposed to mean? What does that supposed to mean? So see what is the we are talking. So see see now, come. So this is your body, right? This is your body. Now I am applying a force. I am applying the force, and what I am assuming, or what I am thinking, that this force, if within the limit of proportionality, P is within limit of proportionality. P is within limit of proportionality. Okay, limit of proportionality. Okay, so now see what is going to happen. What is going to happen if this P is in within the limit of proportionality? Okay, so if you are going to see, if you are going to observe any particular section, if you are going to observe, see, let me take a section here. Okay, so if I take a section here, see how it is going to happen, so let's see it in three dimension. I'll give you the right stress. Normally people don't explain it. So see, this is like this. So if our body is like this in three dimension, see, if I apply a force here, let's suppose I am applying a force here P, and we are having a force here P also. Okay, Now see, if I cut one section of this particular thing or this particular body somewhere, anywhere I could do, but let's suppose I am going to cut this somewhere here. Okay, so I have cut it somewhere here. Okay, now when I cut it somewhere here, when I cut somewhere here, so if I observe, if I see it now in two parts, I take the cut section. If I see it in two parts, see how it is going to behave, how it is going to behave. So it is going to behave like this. See, it is going to behave like this. Okay, see. So see, it happens to be like this. Please try to understand. So this is P. This is the force P here. Now you will observe that this particular part, if you see this particular section, you will see that each of the point of this material on this section, or for that matter any cut section that you are taking, so you will see that a small force delta fx, let's suppose delta f or delta f, delta f, delta f. So every point, see, or the material, see what happens. So there is a big chunk of material, it's a bulk mass, right? So when we are having this bulk mass somewhere, now what happens when you are applying force? So every molecule or every particle, every single particle of this molecule or this material, every single particle is of this material is resisting this external force. uh, Tim, hello, very good evening. So, my dear, we are dealing here with the properties of solid. We are talking about the stress and strain, and after it will be, yeah, I'm explaining. I'm explaining only. See, I'll just give you a brief what we are happening. First of all, my name is Dr. Shankar Sir, and I'm a physics educator. Okay. So, what we have started today is, so we have started with the properties of solid. Now, the first thing is how this properties of solid chapter is different from the previous chapters that we have read. Okay, so this is not the first time. So this is your 11 physics part 2, chapter 1, isn't it? Now, before this chapter, have you done previously? Have you dealt with the forces before? Isn't it? Yes, sir. We already have dealt to some extent with the forces, sir. We have dealt with the Newton's law of motion, NLM. We have dealt it in, this rotational of rigid bodies. Okay, okay, gravitational force also we dealt. So forces we were dealing before this chapter also. Now in this chapter, what is the effect of the force that we are going to deal? Okay, okay, so that is what we have explained you firstly in this session, that if on a body some load, let's suppose P is applied like this, so this body is going to show a displacement. Now, if it is going to show a displacement, then you will be talking about the kinematic part of it, then dynamic part of it. You will talk like this, that this body is displaced due to this force from this point to this point. Now, if this is the displacement, you can find the velocity from it, then afterward acceleration, and you apply the F is equal to ma. So before this chapter, you are dealing with the forces like this, isn't it? Yeah. Okay. Now in this chapter, see what happens. Now try to feel it that on a body, you think that we are applying the forces like this on both the ends, right? Like this P and P. So do you feel that now it is not going to change its position? Okay, but what is going to happen? It is going to get elongated. It is going to get its shape is going to get changed to some extent. Okay, or same thing we can see by fixing. So when we fix our body from one end and then we apply the force on the other end, what is going to happen? Again, it is a case of two equal and opposite forces. Do you agree to it? So in this part of physics, we are interested in knowing that when a force is acting on a body, when a force is acting on a body, what is going to be the change of its shape, or what is going to be its deflection or deformation, that is in this case I referred to as at delta. Previous to this, we have been dealing with the assuming that the bodies are rigid bodies in which when force is applied, they don't show any change of shape and size. But there is no such body in the world, right? You have dealt with the springs also. You never have spoken about like what is going to be the displacement of the spring and all, isn't it? Right? So in this particular part of physics, we are going to, or we are basically interested that when a force is applied on this on a body, how it goes for the change of shape and size of this, right? Are you getting my point? Okay. Okay. Now, in this context, in this particular thing, there are two things very important. One is stress and one is strain. So I was explaining the meaning of the stress. So see, what is the stress? So if you see the definition, and we might be knowing the definition also. So stress is a physical quantity which comes under play when a force that is applied on a body is somehow causing the change of the shape or size of the body. Is causing the shape change or size change of the body. Okay. So basically, if we define the stress, we call it internal resisting force per unit resisting area. Okay. And P is the force that we are applying. If the force we are assuming that it is applied within the limit of proportionality. What is limit of proportionality? I'll just explain to you. But before that, I try to explain that what is the meaning and what is the relevance of this and how we can feel this stress. Okay. So see, when a force is applied on a body, when a force is applied on a body, each and every point of this body is start resisting that force, right? Now if you see a cut section of a body, what is going to happen? What is going to happen on each of the point of this material or this section? There will be a small force on each of the particle, and then they cumulatively trying to resist this force. They are cumulatively trying to resist this force. So normally the definition which is not given in your books, that is the real definition. So stress mathematically is defined as limit delta A tends to 0 delta F upon delta A. This is the real definition of a stress. Okay. Okay, normally people don't tell you. So this is the real definition of stress. That stress is limit delta A tends to 0 delta F upon delta A. Okay, so it is kind of signifies that what is the resistance offered by each of the particle, each of the point when a body is acted upon by some external force which tries to change the shape of the body, which tries to change the shape of the body. Okay. Now from here, see, we can write sigma is equal to df upon dA. Sigma is equal to df upon dA. Okay. Okay. Now from here, we can write df is equal to sigma into dA. Sigma into dA. And if I integrate this, I'll be getting F is equal to sigma into A. So sigma will be, that is stress will be force upon area, and this force is what we call as the internal resisting force, but actually it is average internal resisting force because it is the integrated one, internal resisting force. Okay, so from here comes the definition. From here comes the definition of from here comes the definition of the um, stress. Okay. Okay. Now remember, within the proportionality limit, what is the proportionality limit? So it is very near to actually elastic limit. Padmavati will be talking about the shear strain. I'll be coming to that. Okay, just let's first try to understand the stress. Afterwards, I'll be just speaking of the shear strain also. Everything I'll speak of. Okay, and by the way, welcome to the session. My name is Dr. Shankar Sir. So anyway, so stress is what? Internal resisting force per unit resisting area. Now please understand this. So see, when we say that we are in the within limit of proportionality, when we are within the limit of proportionality. So within the limit of proportionality, what you can do? See, I'll explain what is the limit of proportionality. So within the limit of proportionality, okay, uh, is there any glitch? I'll just see. No. Thank you for telling me. Okay. So see, within the limit of proportionality, what happens? Within the limit of proportionality, what happens? So within the limit of proportionality, see what we can say. Within the limit of proportionality, हाँ बनवाती बिल्कुल क्वेश्चन भी देंगे थोड़ा कॉन्सेप्ट समझ लें है ना सो विद इन द लिमिट ऑफ प्रोपोर्शनैलिटी व्हाट वी कैन से जो डिफॉर्मिंग फोर्स है दैट मीन्स द एक्सटर्नल फोर्स is equal to the internal resisting force is equal to the internal resisting force okay uh, thank you Ishika thank you Devil so within the limit of proportionality what happens so we can assume see it is not always true within the limit of proportionality only we can assume that the external force that is this P and internal resisting force that is F are equal and that is why we use so when we are finding the stress we can say it is P upon A right it is P upon A right that is external force per unit area understood and what is this limit of proportionality? See, don't confuse it with the limit of elasticity. Limit of elasticity and limit of proportionality are two different things. They are what? They are two different things, my dear. They are not the same thing actually. Okay, students assume it to the same thing, but it is not. See, what is the limit of proportionality? So I'll be, telling you about the limit of proportionality, limit of elasticity in the stress strain curve. But now you can understand it that see when we are applying the force on some body, initially it is going to show the strain which is in linear proportion to the stress generated in the body. Okay, and limit of elasticity or elasticity is something if a force is removed. Okay, so see what happens when you are putting force on somebody. When you are putting force on somebody, okay, so you might have observed that the if we remove the force, if we remove the force at some point, okay, if we are applying the force and the force is removed, if the force is removed it's not being that great, but to some extent the force is applied and the force is removed, you might have seen that the body is regaining its original shape. Okay, so elasticity is what? Elasticity is the tendency of a body to regain its original shape. Okay, elasticity is the tendency of a body to regain its original shape. Okay, to regain its original shape when the external force applied on it has been removed. Okay, so when you remove the external force acting on a body, if it regains its original shape, that is what you call as the elasticity. Okay, so see, within the limit of proportionality, we can say that the force upon stress is equal to force upon area. Understood? External force upon area. Now see, now see, now in this case, I'll be naming it, this is what we call as the normal strain, normal stress, sorry. This is what we call as the normal stress. Normal means perpendicular. See, when there is a body, okay, so when there is a body like this, and we are applying the force P here. So basically, this is a two-dimensional way of representing it. It is actually like this. Okay, if you see in three dimension, it could be circular also, it could be like this. Let me consider circular. Okay, let me consider circular. Okay, now see this force when we are applying like this, so we call it normal. Why first of all we call it normal? Now please understand this. This is your cross section. This is your cross section, right? Now if you observe this pen, so this is my digital pen from which I write. So if you observe this pen, you will see the length. You will see the length, right? Okay, you are going to see the length, and this is what? This is the cross section. Okay, this is the cross section. Okay, okay, this one, length and cross section. So whenever, see, when we say shear strain, when we say normal stress, shear stress or strain, we are referring it with respect to the cross section. Basically, we are referring it with respect to stream is lagging me. Oh my goodness. I'm hoping it is better now. Okay. So what I was saying, hello Bhuvan. So what I was saying, so when we call any force or any stress, any strain normal, shear, longitudinal, it is basically with respect to the cross section. So basically when we say that the stress is normal, so we are referring to the stress that is acting here on this surface, okay, on the cross section, because the force is, yeah, the forces which is perpendicular, the forces which is perpendicular to the cross section. So that is why it is causing a normal stress on the plane of the cross section. Okay, so this normal stress will denote generally by sigma, and it will be P by A. Okay, now due to this force, it is fine now. The stream is fine, I guess. Now, when this force is applied, as I said, so this is what? This is your stress, and we'll call it as normal stress. We call it as normal stress, right? Now, see, now due to this force, this body is going to be stretched. It is going to be like this, okay? This is going to be stretched to some extent. This is going to be like this, and this is going to be, the length is going to be increased. Okay, the length is going to be increased, right? Now, what is the strain? What is the strain? So, if I define the strain, so strain is change in dimension. Strain is change in dimension upon original dimension, upon the original dimension. Like for example, in this case, as you see that the length is having some change. Okay, so if I say the change in the length, if I say the change in the length, so it will be the delta, and what is the original length? That is the L. So it will become delta by L, and you call it, see, you call it longitudinal strain. So why you call it longitudinal strain? Can you tell me, the live student? Longitudinal strain, okay, and we are going to denote it like this, epsilon. So why we call it longitudinal strain? Can you tell me? Anyone? Can you tell me, anyone? Why we call it longitudinal strain? Now, when I ask this question to a student, they say, sir, it has happened to be in the length. Since it is happening in the length, this is longitudinal strain. Since it is happening in the length, that is why it is called the longitudinal strain. So, beta, this is not like this. See, when we are calling it a longitudinal strain, basically it is because it is the strain in the length which is parallel to, it is the strain in the length which is parallel to the direction of the load. It is parallel to the direction of the load, right? Okay, so what we are going to call it? We are going to call it a longitudinal strain, and we are going to show it by epsilon. We are going to show it by epsilon. Okay. Did you get this point, the live students? Please tell me if you have got this point or not. Yeah. So when the force is acting in some direction, right, and it is causing the normal, right? Okay. So when it is normal to some plane, when it is normal to some cross section, when it is normal to some cross section, and the strain happened to be in the direction parallel to the direction of application of force, we call it longitudinal strain. Okay. Okay, so see, if I compile all these things, see what is happening. See what is happening. So let me summarize it. So we are having a body like this. On this, a force is applied like this, right? Its original length is L. Now in this case, and let's suppose it is having a diameter D. It is having a diameter D. Okay. Okay, now in this case, see what is the takeaway point. So first of all, this force, when you see it like this, it is basically normal to the plane of cross section. So where you will get a normal stress, and within the limit of proportionality, or you can say that you usually say limit of elasticity, within elasticity, right? Within elasticity. So it says that stress is equal to the normal stress is force upon area. What is going to be the normal stress? So it is force upon area. Now what is going to be the longitudinal strain? So it is change in length upon original length. This is going to have some change in length, right? Okay. Now I want to ask you something. So this is what we call as the longitudinal strain. This is what we call as the longitudinal strain. Okay, this is your longitudinal strain. So it is the strain in the direction parallel to the application of the load. Now you understand this. So see what happens when we are stretching something, when we are pulling something, when we are applying force on a body like this. Do you feel that it is stretched? That means its length is increasing. But when its length increases, its cross section dimension decreases. Do you believe it or not? Yes or no? Huh? It happens or not? So if this is the body like this, if this is the hmm, yeah, something is wrong. I don't know. Okay. So basically, it is the longitudinal strain. So now, what I was saying, so whenever a body is some sort of stretched, it is stretched like this. Okay, it is stretched like this. It is in tension. Tensile force is applied. So when the length is increasing, do you feel its cross section dimension is going to get decreased? Yeah, definitely, sir. Okay, so basically, it is going to attain a shape like this. It is going to attain a shape like this, right? It is going to attain a shape like this somewhat. Okay. Okay. Now in this case, see what we can do. So the live students can respond to me if you are getting it or not. So now in this case, there will be some strain in this diameter also, na? Or in this cross section dimension also. Can we say that? There will be some decrease. There will be some change in dia also. Now here I'll be introducing you with one term and I'll call it as epsilon L, and we'll call it the lateral strain. Now what do we mean by the lateral strain in this context? So the lateral strain is basically the strain happened in the direction perpendicular to the direction of the load. It has nothing to do with the diameter. It has nothing to do with the diameter or the length, but it is called lateral because this strain is in the direction, perpendicular. It is in the direction perpendicular to the direction of loading. Perpendicular to the direction of loading. So when it is perpendicular to the direction of loading, we call it epsilon L. Okay, we call it epsilon L, and this is given by, change in dia upon original dia. Okay, so let's suppose this is changed to d minus delta d. Okay, d minus delta d. So see, what is the strain, sir? It is change in dimension upon original dimension. So whatever dimension is changed due to the loading, there is some strain in that direction, right? Like in this case, the d is reduced. So we have some lateral strain also that is given by the change in diameter upon the original diameter. Okay. Okay, so what are the takeaway points? So when a force is applied like this, we can now know the formula of the stress, we know the formula of longitudinal strain, and we know the formula of lateral strain. And the tendency of force is normal. It is perpendicular to the plane of the cross section. So the same thing can happen. They can give you any orientation. They can make a body like this. Okay. They can make a body like this. Okay. They can make a body like this. Right? Anything they can do. They can make a body like this. Right? Okay. So let's suppose a force P is applied here. A force P is applied here. Okay. A force P is applied here. Right? Anyway, the force P being applied. So it will cause, see here you have to be careful that it will cause the normal stress on which surface. So for example, in this case, if this is a body like this, okay, let us extend it to the third plane. So on this plane, it will give the normal stress, right? This plane, this is going to give the normal stress. In this case, this is the force. So when I'm showing it 2D, it is basically somewhere in the middle of this phase. So this normal means perpendicular. So this normal stress is going to be on this phase. In this case, it is on this phase. So no matter in what orientation you are using it, okay, it is always sigma is equal to force upon area. Remember, this area is the one which is normal to the direction of the force, because this is the normal stress. And due to this normal stress, we'll have a longitudinal strain. Like for in this example, let's suppose all the length which is parallel to the direction of the loading are L. Okay, so we shall call the longitudinal strain as change in length upon original length, that is delta upon L. And there will be one thing, that is the lateral strain. So it is the strain in. So if I say like rectangular body I have shown, so this is X, this is Y, this is Z. Okay, this is Y, this is Z. So see, I'll not confuse you in this. So what will be the change in length? So let's suppose the other two dimension in each of the cases is B and D. Okay, so the lateral strain will be delta B by B. It will also be equal to delta D by D. Understood? Okay. So when a force is acting, I'll just write it here. So epsilon L is going to be the change in width upon original width, that is delta B by B. Okay, or it is also equal to delta d by d. It is also equal to delta d by d. Because in 3D, you see that if you are having the force in one direction, in 3 dimension, if you are having basically the force in one direction, it is basically something is wrong. See, see, okay. Just one moment. So there is some technical. Yeah. So now in this case, the load is applied in one direction. So see, in the direction of load, it will become the longitudinal. So the other two direction, in the 3 dimension case, we have 3 direction. Na? So if you have load in one direction or parallel to one direction, the other two direction will become the lateral one. So it will have the lateral directions as delta b by b. The lateral direction as delta d by d. So this is b, this is d. Right? This is b and this is your d. Right? I hope it is fine to everyone. Okay? So actually, it is not coming here. So basically, it is epsilon L. Right? I am trying to write it epsilon L. Okay? Okay. Wonderful. So if a load happen to be perpendicular or normal to any cross section or any area, you will be able to realize. You will be able to realize. Okay. So basically, what we have come to understand. So when a force is acting normal to any surface area or any plane area, if the force is acting normal to any plane area, basically what happens? You can have the normal stress. You can have the longitudinal stress strain. You can have the lateral strain. Okay. Okay. Now, where the Hooke's law comes into play in this, right? So basically, as I said, as we are dealing with the Hooke's law, as we are dealing with the Hooke's law, So basically, if you see that we have assumed that the load is within the proportionality limit. So what Hooke's law has stated? So Hooke's law said corresponding stress is proportional to 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 corresponding strain within the limit of proportionality okay, within the limit of proportionality. Okay, so within the limit of proportionality. Okay, so corresponding stress is proportional to corresponding strain within the limit of proportionality. So that means, see, normal stress, see how we are going to relate. See what we are relating with the Hooke's law, please try to understand is. So the normal stress is related with the longitudinal strain. Stress is proportional to strain, right? So till now we have spoken about this. Okay. Now similarly, we will be talking about the shear stress also. So the shear stress is proportional to the shear strain. Okay. And the volumetric stress is proportional to the volumetric strain. And this happens to be within the limit of proportionality. Remember, Hooke's law is not defined for or not given for the limit of elasticity, but it is given for the limit of proportionality. Okay, so normal stress is proportional to longitudinal strain, shear stress is proportional to shear strain, and volumetric stress is proportional to volumetric strain. So this is going to be stress. So when I let go of the sign of the proportionality, we know our constants come into picture. So that constant we can call it as E. Okay, when I let go of this proportionality, there will be a constant coming, we can call it G. And when this goes, we have a constant that is K. Okay, that is the K. So what is this E called? So you call it as Young's modulus. What do you call it? Young's modulus, or you call it modulus of elasticity. You call it modulus of elasticity. Okay, what do we call it? We call it the modulus of elasticity. Now in this case, see what is we are getting, that is G. So G is modulus of rigidity. G is what? It is the modulus of rigidity. Just one second. Yeah. So what do we call it? We call it modulus of rigidity or shear modulus, or what we call it, or we call it the shear modulus. Okay, or we call it the shear modulus. Something. Yeah. So we call it modulus of rigidity or shear modulus. See, there is a little technical glitch. That is why it happens this way. I'm very sorry. So this is going to be the shear modulus, and this K is what we call as this is your bulk modulus. This is what is, this is the bulk modulus, right? So basically what Hooke's law does, okay, what is the Hooke's law? So Hooke's law basically relate some type of stress with their corresponding types of strain. So as we have explained that what is the normal stress. So when a body is like this, and the force is applied this way, the force is applied like this. Okay, so this is the body and this is the force applied on this body. So this is going to show you what, and one side it is fixed. So this is going to have a normal stress, that is force upon area, it is going to have a longitudinal strain, that is change in length upon original length. So Hooke's law relate these two things, that is stress is proportional to strain, normal stress is proportional to longitudinal strain, and from here we can write P by A is equal to E delta upon L. So we can write delta is equal to PL upon AE. Delta is equal to what? We can write delta is equal to PL upon AE. I hope it is fine to everyone. Yes or no? Please tell me. Yeah? Okay. Okay, so from here you can find the deflection using this expression, that is PL upon A. So if you are having the load on a body, the length, the area, the Young's modulus, you can do like this using this formula. Okay, so I'll just give you one question so that we are able to apply this formula. Yeah. So let us try this question. The live students can try this question and answer me in the chat. So the live student, please respond to me. What is the solution to this question? How can we do it? Please try answering it. Yeah, 1 GPa is 10 to the power 9 Pascal, Newton per meter square. Okay. Or you can write it as 10 to the power 3 megapascal, because when you say 1 megapascal, it is directly equal to uh, you know 10 mega 10 to the power 1 Newton per mm square. Okay. See, 1 Pascal is 1 Newton per meter square. Okay. 1 megapascal is 10 to the power 6 Newton per meter square. Okay. And 1 GPa, that is 1 gigapascal, is 10 to the power 9 Newton per meter square. Right? It is 10 to the power 9 Newton per meter square. Or you can write this as 1 Newton per mm square, because see, in 1 meter there is 10 to the power 6. Yeah, that is what you have to apply. Okay, and this is going to be, you see, 10 to the power 9, so this will become 10 to the power 3 megapascal. Okay, so you can do it like that also, you can do it like any way you want. So I recommend that, see, when you are having to give the answer in mm, it is more beneficial that you change the units to this uh, mm. Yes, it is, but again, that is not very much required. Yeah, 10 to the power 3. 1 kilo, we already know. Okay. Now, see how we can solve this question. So, let us try. What is the answer to it ultimately? What is the answer to it ultimately? What do you mean by compressive load? So, if something is getting stretched, it is by the tensile load, and when it is getting contracted, it is by the compressive load. Very simple question. And since there is some technical issue today, so I'll be ending with this question and I'll continue from this point in the next session. Please do it. The live students, I'm waiting for your answers. See, what is tensile, what is compressive? So basically, when a force applied on the body is tend to increase the length of the body. When a force applied on a body is tend to increase the length of the body, we call it tensile, like this. This is your tensile. Okay, which causes the elongation of a body. Right now, when there is a body and a force is applied like this, there is a body, a force is applied like this. Okay, like this. So this is having the tendency to contract the body. This is what we call as the compressor. And we can always choose a direction sign to it also. So what could be the sign we can choose? So for tensile and elongation, see, we'll be using the positive, and for load that is towards the body, okay, which is trying to contract, occur the contraction on somebody, we'll use the negative sign for it. Okay. Now please solve this question. Let's see. See, we can do it. No worries. Got it? Wonderful. Any answers then? What could be the answer? What could be the answer? What is the answer to this? The live student. Any one of you can answer at least. Very simple question. Just plain use of the formula. See, I wanted to get into the tricky concepts today. I wanted to complete the whole thing today itself, but I don't know what is the technical issue. Some sort of glitches is happening again and again. So after this question, I'll be leaving you. But I want at least one of you to solve it. Please go for it. Try. Please try it. Anyone? Anyone? Any answers? To see how we can deal with it. So it says a steel bar of 40 mm cross 40 mm cross section is subjected to an axial compressive load of 200 kilonewton. Okay, so there is an axial load of 200 kilonewton. So when they say axial load or something like this is like this. Length is given, that is 2 meter. They are asking you the elongation. So we understand that delta is equal to PL upon E. We just have sorted this equation. So P is 200 into 10 to the power 3. L is 2 meter, that is 2000 mm upon area. Area is 40 cross 40 and Young's modulus is 200 GPa, that is 200 into 10 to the power 3, right? 10 to the power 3. So now when we see, so see what we are getting. So we are getting, so 4 and this is 4 16 to 32. So it is somewhere near 1.25 that we are getting from here, right? Okay, so when you do the calculation, you will be getting 1.25 mm. You will be getting 1.25 mm. Okay, 1.25 mm. I hope this is fine to everyone, right? Okay. Okay, so see, this is to some extent how you can apply the Hooke's law. So guys, I'll be keeping it to this point in this session only. Sorry for some technical glitches. In the next session, I'll be coming up with the properties of bulk materials. Okay, that is this only, and I'll be explaining you to some more extent the Hooke's law, elastic constant, Poisson ratio, stress strain curve, right? Everything that you require with many questions. So with this, thank you.